Now we go to 9.46. An airplane is landing with velocity v0. Here is a wheel of the airplane. It has a mass m, and it has a radius r, and omega equals 0. The wheels are not rotating. And so every point of the wheel has this forward velocity v0, also the center of mass, and also the bottom. And as it touches down, there will be a frictional force, because it's slipping with the runway, and this frictional force will be a maximum at touchdown. This is before, just at the moment of touchdown. And there is a moment of inertia about this axis, about this rotation axis, which is I. Now let's look at the situation after this wheel has come to what we call a pure roll. What does it mean that it has come to a pure roll? Here is that wheel, and here is the runway. If this wheel has made one full rotation, I'll make a little mark here, and this mark appears here again. It has made one full rotation. If the distance between the center of mass equals 2 pi r, if this is r, then we call this per definition complete pure rotation, pure roll. There is no slip. And you can easily see that, because the circumference here equals 2 pi r. The time to go around, t, that is the period to go around, is 2 pi divided by omega. And so the velocity of the circumference is obviously 2 pi r, the time divided by the time that it goes around, and so the velocity of the center of mass must be equal to omega times r. So the velocity of this center of mass, this is the velocity of the center of mass, is 2 pi r, that's the distance that it moved, divided by the time for this object to go around. And 2 pi divided by t is omega. So you see here that the pure roll condition, and the sufficient condition is that this v of the center of mass must be omega r. That is the pure roll condition. Then we have no longer any slip. We have an angular velocity omega now, and this radius is r. Well, you can do the same problem by taking a ball, a billiard ball, and you can shove the billiard ball on the table so that there is no rolling action, and then after a while you will see that the billiard ball is going to go into pure roll situation. It may not be so easy to demonstrate that to you, but I have a ball here. And if I were to move the ball, to slide it along, so to have exactly this situation, then when I do that and let it go for a while, it goes into pure roll. It's already in pure roll. It goes very quickly in this case. You see, I'm shoving it, and it is the friction that torques it up to go into pure roll. So let's massage this further. This is not so easy. In fact, I was not able to do this problem in a very simple manner. I'm trying to find my drawing. Where is my drawing? My goodness. Well, I will have to make a new drawing. I can't find my drawing. When it touches down, there is this frictional force, and this is the radius r. First of all, we have to obey Newton. F, which is this force, so I will just write down this force, equals m times a times the center of mass. This is the center of mass. That's non-negotiable. That always must hold. V of the center of mass must be V0 minus AT, which is the same A. And notice this minus sign already takes into account that the wheel is going to be decelerated. In other words, A, as a result, will be positive, because the minus sign is already built in. then I have V center of mass at any moment in time that I am in pure roll must be omega t times r. That's my pure roll condition. Then I have that the tau relative to point C equals r times f. Torque is in this direction. That's why it will try to make omega increase in this direction. So that is r times f. And that is also, by definition, the moment of inertia about this axis times alpha, which is the omega dt. This is equation number 2. This is equation number 3. The situation is getting out of hand. This is equation number 4. And then omega t, which is spun up, is omega 0 plus alpha times t. Omega 0 is 0 at the moment of touchdown. And I have assumed here that a is constant and that alpha is constant, but I didn't even have to assume that. As you will see, I'm going to eliminate a, t, and alpha and convince you that the final result is independent of a and t and alpha. If the plane pushes harder down on the wheels, the frictional force will be higher, and the acceleration, the deceleration I should say, will be larger. Well, the only thing that will happen is that this pure roll situation will occur earlier, but the final result is still the same. Look at these equations. I first want to combine this one with this one. And what I'm going to do, I'm going to eliminate f. And when I eliminate f between this one and this one, I'm going to get r times m times a equals I times alpha. And now I'm going to eliminate alpha by using this equation. So I'm going to write down omega equals t equals r times m times a times t divided by I. This now, omega t, according to this equation, is also V center of mass divided by R. I will just write V for that. That is simpler. Just as I have dropped A, also the center of mass. So this now must become V divided by R. Therefore, AT becomes V times I, V being the final velocity of the plane, divided by mr squared. And this AT, I'm going to substitute now into this equation, and I think I have done the job. It was a lot of massaging and it was a lot of work, but I think it will work. V equals V0 minus V times I divided by mr squared. And so I find then that V, the final velocity of the plane, equals mr squared times V0 divided by mr squared plus I. A non-intuitive result. What you see is that the larger I, the moment of inertia of the wheels, the smaller V will be. And that I find kind of intuitive. Because if I is very large, when you are in pure roll, you dump a lot of energy into that wheel. Remember, the kinetic energy of a rotating wheel is 1/2 I omega squared, and you have taken that out of the motion of the plane. So I like the idea that a very large value of I gives me a low velocity of V. Notice again, there is no frictional force in here, there is no A in here, there is no alpha in here, there is no T in here. And as I stressed earlier, the A, the alpha, the T, and the F can change in time. And if the frictional force is enormous because the plane pushes hard, well, the whole process will go very fast, but the outcome is not changed. Not so intuitive.